Got it. So I would like to welcome everybody to our restart of our non-commutative geometry seminar. So it's Europe, Asia part. And considering the fact that there are so many different online seminars and being hopeful that we can start meeting in person. So we also have not online but real live seminars. We decided to do this one once every 2 weeks. So we are starting today, and the next one and the following ones will be every second week. So our speaker today is Stefaan Vaes from KU. It's Katholische Universität Leuven. And the subject, well, you can see the title. So Stefaan, please.
Thank you very much, Richard, for the introduction. So it's a great pleasure to give this talk in the non-commutative geometry seminar. And I will be reporting on a recent joint work of Daniel Drimby and myself. And I will actually right away put the main result, because the main result is actually kind of easy to state, because it's a very concrete theorem that I will discuss, but then also put it in a broader framework. And the theorem is about specific groups of isometries of the hyperbolic plane. And let's take the model where the hyperbolic plane is the upper half plane, H2, and then the group of isometries is PSL2R, acting on it by these fractional transformations, as you know. And what I'll be interested in is in how subgroups of PSL2R, countable subgroups, act on H2 and how their von Neumann algebras look like. And here is the main theorem, but this is actually a sample theorem of a general phenomenon that I will be discussing. And we will look at specific arithmetic lattices. I will come to that later. And let me start by the most basic case. So we will look at dense subgroups of PSL2R. And let's take these very particular ones. We take PSL2 of Z, to which we add a certain number of allowed denominators. So we add certain inverses of prime numbers. This gives you a ring, Z to which we have added as inverse. And this creates, at least if S is a non-empty set of prime numbers, a dense subgroup of PSL2R. And this group is then acting on H2. And I build the cross product von Neumann algebra. So this is an infinite measure preserving action. So that it's an isometric action with preserving the canonical measure of H2. And so this is in principle a 2 infinity factor. And this 2 infinity factor behaves in a very interesting way on the number of prime numbers we have added to Z. So let me start by, of course, the trivial case, but just to make the story complete. As we, of course, well known, I mean, if I don't add any prime number, PSL2Z itself has, of course, a fundamental domain when acting on the hyperbolic plane. So therefore, the von Neumann algebra completely trivializes. Now, if I add only one prime number, we will see that the result is a 2 infinity factor. It's not amenable. It's a non-injective 2 infinity factor. But it's not at all rigid. So this will be a talk in the context of rigidity theory a la Sorin Popa. And in that case, for instance, the same von Neumann algebra can really be realized by enormously many different group actions as cross products by many, many different group actions. And once you add at least 2 prime numbers, the strongest kind of rigidity happens, namely, one can actually entirely recover both the group and its action from this cross product to infinity factor. And we can actually prove that in that case, if that von Neumann algebra happens to be realized in any other way as a cross product, essentially the groups must be the same and the actions must be the same. Essentially here is hiding that we can do some induction. I mean, but that's really essentially it's recovering the group and the action from the 2 infinity factor. So this is the main theorem that I would like to discuss, but I will of course put it in a broader context so that I can also give you some ideas. So let me discuss first some terminology about, say, isomorphism of cross products and isomorphisms of equivalence relations. So we are really looking at groups that act essentially freely. So almost every point will have a trivial stabilizer. We will most of the time assume that the action is ergodic, and we will assume that sets of measure 0 remain of sets of measure 0 under the group action. So that's what we call a non-singular action. And most of the time we will have actions that actually preserve either a probability measure or an infinite measure, as was the case with the hyperbolic plane. Now, when I was saying that two actions, that an action can really be recovered from the ambient to infinity factor in that case, it's really because we get the action up to conjugacy. So really actions being completely the same is this obvious notion of isomorphism, where both the groups and the action are completely isomorphic. A weaker notion is the notion of orbit equivalence, where we say that actually the orbit equivalence relations are the same. And that amounts to saying that there is an isomorphism preserving sets of measure 0 between x and y, sending almost everywhere orbits onto orbits. So that's really the same as isomorphism of the orbit equivalence relation. And then finally, W star equivalence of the actions is by definition isomorphism of the cross product von Neumann algebras. So this is yet another, an even weaker notion of, say, equivalence of the two actions. And then getting back to the conclusion of the previous slide, the strongest type of rigidity that we are after in this context is to say that a group action is W star superrigid if whenever the same von Neumann algebra cross product can be realized by another group action, this does imply it forces the group action to be conjugate to the original one. And then once again, I mean, especially if you deal with infinite measure preserving actions, you have to deal with certain amplifications, but still you can exactly say which other group actions may give rise to the same von Neumann algebra. So that's the topic we are looking at. And this is a notion and also a number of results that really fit into so-called deformation rigidity theory of Sorin Popa. And so let me start by quoting one of the earliest results of this nature. And that goes back really to the foundational paper of Sorin in 2003. But then to state or to prove really what is stated here on the slide, one has to go to what Adrian Ioana did, and then also joint work of Adrian and Sorin and myself by now more than 10 years ago. And so this is really a prototype of this superrigidity phenomenon happening for Bernoulli actions. So if you have a group gamma that acts by its Bernoulli action, so you take a base probability space and you act by shifting the infinite product. For a technical reason, let's assume that the group is, say, infinite conjugacy classes or has no finite normal subgroups. And then there are two cases that ensure that the action is superrigid, namely when gamma has Kasdan's property T, or when gamma is a non-trivial product group, namely when a product of an infinite group and a non-amenable group to be sufficiently non-trivial. And why am I mentioning this? Because it already gives me an occasion to quote what is really the most fundamental part of the whole deformation rigidity theory. It's extremely visible in this example, where both the deformation and the rigidity are actually very, very visible. And the deformation is Sorin Popa's notion of malleability. So what is malleability in this context? The action, not the group, but the action is extremely deformable in the most extreme way. Namely, it's possible to have a one parameter family of automorphisms of x times x. So you double the action. So you double the action, you consider its diagonal action on x times x in this way. And this is extremely deformable in the sense that there is a one parameter family of automorphisms that commute with the diagonal action. And they move from the identity to the flip. So it's really like moving the action to its orthogonal, and that is the first key ingredient that one combines with the rigidity property that comes from either property T or a spectral gap rigidity, and spectral gap will come from this kind of non-amenable groups acting in a Bernoulli setting. Of course, this is extremely vague. I will make this more concrete in a minute. So how can one try to prove that kind of results? How can one ever try to prove that you can recover a group action from such a cross-product von Neumann algebra? So there are actually two ingredients to do this. And the first one is that you should essentially prove that this cross-product has the canonical subalgebra L infinity of X as its unique Cartan subalgebra up to unitary conjugacy. So Cartan subalgebra is a maximal abelian subalgebra as L infinity of X that is moreover regular, so its normalizer generates the entire cross product. And in certain cases, but this is actually quite hard to establish, a von Neumann algebra has a unique such Cartan subalgebra. So this then forces, if you can establish point one, it forces any other cross product that is isomorphic. You can then choose the isomorphism to preserve the canonical subalgebra L infinity of X by uniqueness. And thus the isomorphism induces so-called orbit equivalence of the actions. And therefore in step two, which is a kind of independent step, you have to prove that from the orbit equivalence relation, you can actually recover the group and the action. Now also that follows a typical path, but with one difficult step, of course. How can you ever try to prove this, that you can recover a group action from the equivalence relation? Well, so you assume that another action is orbit equivalent. So you are given an isomorphism of the spaces sending orbits onto orbits almost everywhere. So since the action is essentially free, such an orbit equivalence comes with a so-called Zimmer one cocycle, namely delta should map Gx to some element of lambda applied to delta x. Since the action is free, there is a unique such element that I call omega of Gx, and this induces a one cocycle. So this is the one cocycle relation. Now the word one cocycle may give the impression as if there is some kind of cohomology theory behind, but that's not actually true. I mean, you cannot even, if lambda is a non-abelian group, you cannot even multiply to such cocycles or add to such one cocycles. It's really just a one cocycle. But there is a notion of cohomology at least, but no true cohomology theory. So two such one cocycles are said to be cohomologous if there is a map measurable from X to lambda that relates the two. And then the final observation is that, of course, there is a very specific kind of one cocycles, namely one cocycles that are independent of the X variable. Now, a one cocycle that's independent of the X variable, that's just a group homomorphism, of course, from gamma to lambda, that will always satisfy this relation as a function not depending on X. And the whole point is that you hope and try to prove in specific contexts, and this then really goes back also to famous work of Zimmer in certain cases, you try to prove that the one cocycle omega that comes from the orbit equivalence is automatically, for some reason, cohomologous to a group homomorphism. And then you're in good shape to prove that actually the actions must be conjugate. So here is the famous Cocycle superrigidity theorem of Sorin Popa. First, there is the definition. So we say that a non-singular action is cocycle superrigid if actually any one cocycle with values in any countable group happens to be cohomologous to a group homomorphism. So this is, of course, the strongest you can hope for. And it is essentially true. And again, the essential is hiding certain amplification issues that if you can prove both at the same time, if you can settle the uniqueness of Cartan problem, and if you can prove Cocycle superrigidity, then actually you have proven that the entire group action can be recovered from the ambient Van Neumann algebra. Now, the famous theorem of Sorin Popa from 2005 and 2006 is that exactly the actions that we were looking at before, namely Bernoulli actions of either Cartan property T groups or non-trivial product groups, are Cocycle superrigid. So there is actually an interesting conjecture here, how broad this class of groups is for which the Bernoulli action is Cocycle superrigid. And the conjecture is that this actually holds even only if the first L2 Betty number of gamma is 0 and the group is non-amenable, of course. But that conjecture is quite wide open, I would say. So to give a slightly more concrete flavor of Cocycle superrigidity and Popa's deformation rigidity theory, I will give you in one slide a brief idea where this kind of Cocycle superrigidity comes from, because the same technique will pop up in what I want to present to you as new work. So here is just the same theorem again. We have a Bernoulli action, either of a product group or of a property T group. And you take any one cocycle, so it's very general, any one cocycle with values in the countable group lambda, and we again look, as I said, to this double action. So gamma is acting diagonally on x times x, and therefore, this is still completely general, you can define for these diagonal actions, this diagonal action, two one cocycles, namely one that only depends on the x variable and the other one only depending on the y variable. Now, as I said, Bernoulli actions have this malleability property, so you can like turn the identity to the flip in a way that commutes with the action, and therefore we actually get a one parameter family of one cocycles. Depending on this parameter t, we have all of these as one cocycles for the diagonal action. Now, because of the spectral gap property, there is this general phenomenon that actually goes back to even Alain Cohn's theorem on the fundamental group of two unfactors with property T, where you have the phenomenon that if now T and S are close to each other, that this will force these two one cocycles to be cohomologous. There is no way to continuously deform in a way. Now, then of course, there is some work to do, but it does imply, this does work, and it does imply that omega 0 must be cohomologous to omega 1. And if you look again at the definitions of omega 0 and omega 1, you can kind of believe, but again, there is a theorem to prove that the only way that these two things can be cohomologous is really because it was essentially independent of the space variable. And that's actually really the conclusion. And therefore, the one cocycle is actually cohomologous to a group homomorphism. So this is the essence of Popa's theorem. Now, variants of this technique have been used like at many occasions and are used again in the theorem of Daniel Grimby and myself. But to explain you this even better, I will show you another instance of a different type of deformation that led to similar results. So here is another very nice Cocycle superrigidity theorem due to Adrian Ioana, and I will only state it in a special case. I will come back to that later. It's a completely different type of actions as the Bernoulli actions, because this time we will be looking at profinite actions. Namely, we have a totally disconnected compact group, and we have a dense subgroup, and gamma, and we look at the action of gamma on K by left translation. This is completely orthogonal to Bernoulli actions. So Bernoulli actions, they are entirely not compact, yeah, in any way. And the theorem that Ioana proved is that if gamma has property T, then any such translation action with K totally disconnected and compact must be virtually Cocycle superrigid. And virtual in this context means that it's up to finite index. So a one cocycle need not be exactly cohomologous to a group homomorphism, but it will be the case after you restrict it to gamma 0 times k0, where k0 is an open subgroup and thus a finite index subgroup of the compact totally disconnected k. And then gamma 0 is the corresponding finite index subgroup of gamma. So if you want rather a concrete example, what you could do is to take SLN Z in SLN of the p-adic integers for n at least 3. So this one has property T, and this is my compact totally disconnected group. And so what is different here is that we are looking at already, as we will do later, at locally compact groups on which we act by translation by a dense subgroup. Now, how did essentially Joanna prove this theorem? And I again want to show you the deformation rigidity idea. So you take any one cocycle with values in any countable group. And again, there is a deformation happening. Since the group gamma is acting by left translation on K, it commutes, of course, this action with right translation. So therefore, for every element in my compact group K, there is a new one cocycle omega K, defined by this formula. Omega of the identity element is the original omega by definition. And again, property T will ensure that there are no small perturbations. So omega K will be cohomologous to omega when the K lies in the neighborhood of the identity. Now we are in a totally disconnected setting. So this does create an open subgroup K0 such that omega K is cohomologous to omega for all K in such an open subgroup. And then again, you have to work, but you have found your open subgroup and you can kind of believe that you have untwisted the cocycle on this open subgroup. So that's the essence of Joanna's theorem. And his actual theorem is more general. It's dealing with arbitrary profinite actions, which would actually mean that you allow yourself to act with gamma on K mod K1, where K1 is a closed subgroup. But that's adding a little layer of difficulty, and it would be more difficult to present the basic idea, but that's more of a technical issue. Okay, let me, before moving back to what is really the new work today, give you one example that's infinite measure preserving, because it shows that other issues pop up in the infinite measure preserving setting. So here is a very natural group action. You take R to the N and you view SLN Z as acting by linear transformations on Rn. They of course preserve the Lebesgue measure of Rn. When n is at least 3, this is indeed an ergodic action actually. When n is at least 2, this is an ergodic action already. And what we prove is that from n starting 5, this is Cocycle superrigid. And then of course you say, okay, how can this be that it's with n at least 5? I mean, you would have believed me with n starting at 3, but n starting at 5 is probably strange. Now, the reason is the following. This is our first, say, encounter with infinite measure preserving actions, and they really behave very differently. So again, there is a deformation. This time it's rotation of Rn times Rn. So of course, we act diagonally on Rn times Rn, and then rotation commutes with this. And the kind of rigidity we need, it's not enough now that the acting group is property T, because since it's like acting on an infinite measure space, you can lose the entire group. For instance, if gamma acts on itself, that's like the group being the trivial group. I mean, we don't consider that as really an action of gamma. So since it's an infinite measure space, there is a notion of property T, but it's property T of the action, property T of the equivalence relation that you really need. In the probability measure preserving setting, that would be equivalent with property T for the acting group. But here it's really for the relation that you need it. And you need it actually for this double. And well, I'm not saying that this is not true for n equal 4 or n equal 3. It's false for n equal 2 though. But at least only when n equals 5 or more this diagonal action has property T. So there is a good reason why we deal only with n at least 5. Okay, that was the kind of basic context and introduction. So let's move back to the concrete theorem that I was discussing. So we are looking at the hyperbolic plane, which is of course this homogeneous space, PSL2R with the compact subgroup PSO2. And the kind of general and if you wish, abstract nonsense setup is in general, you have a locally compact G that we consider, of course, second countable. You have a closed subgroup P, you take the homogeneous space, G mod P, and gamma is a dense subgroup of G acting on G mod P. And in each of these cases, it's a highly relevant question to say, can you prove that in this cross product, L infinity of G mod P is the unique Cartan subalgebra? Can you prove that such a translation action on a homogeneous space is Cocycle superrigid? And then in particular, what does it say on my specific example here? And what we do is to phrase this in a very general way. So Daniel and I, we introduce a general notion of superrigidity, of Cocycle superrigidity for dense subgroups of locally compact groups. So we put ourselves in this very general context. So you take any locally compact group with a dense subgroup gamma, you then have this ergodic action of gamma on G by left translation. And it basically makes no sense to look at plain Cocycle superrigidity. Already with totally disconnected groups, we had to restrict to these open subgroups unavoidably. So the same here. So we color that with the expression essential. So what is essential Cocycle superrigidity by definition? It means that any one cocycle can be untwisted after the proper reductions. So there are two reductions. You have to have the liberty to only do it on an open subgroup. And then secondly, you have to allow that this open subgroup is actually covered in the sense of covering homomorphisms for, say, the universal cover of a Lie group. So there is a covering homomorphism from another locally compact G1. And it's only after restricting to G0 and then lifting to the cover that the thing is cohomologous to a group homomorphism. Okay, this sounds technical, but as we will see, this is the good notion in the sense that this is the kind of thing that is satisfied in many cases. And it does give you what you want in the cases that we are really interested in. So the definition is the abstract thing you can in high generality establish. But then to really make it fruitful, you use the following actually kind of straightforward proposition. Of course, you're specifically interested when G is a connected Lie group and P is a closed subgroup, say connected even, connected closed subgroup. And then you moreover assume that the homomorphism from the fundamental group of P to the fundamental group of G is surjective. And then, I mean, under these little technicalities, and all of this is, of course, satisfied when you look at the hyperbolic plane or other hyperbolic spaces, then actually this essential superrigidity of the subgroup does imply the usual one that we had before for the action on the homogeneous space. Somehow this kind of assumption on the fundamental group wipes out all the intricacies here. And of course, there are no open subgroups because we are in a connected setting and so on and so forth. Yeah. Okay. How did we do this? Well, there is a very general such essential superrigidity property that we prove for dense subgroups of locally compact groups. And the typical thing is the following. We are looking at irreducible lattices. So what happens is that the theorem that we prove is where G is any locally compact group, H as well. You assume H to be compactly generated. And you take a lattice in G times H. Then, of course, you can project this onto G. This gives you a subgroup of G. And now we make two assumptions, and these two assumptions will ensure that, that this subgroup is indeed essentially Cocycle superrigid. And the assumption is that your H is itself a product of two groups. And now we have to put the correct notions of spectral gap and so on. So gamma is a lattice. So G times H mod gamma is a probability space. And H, as well as G, by the way, H is acting on this probability space by left translation. And what we need is that both H1 and H2 act ergodically, but which is a kind of irreducibility property of the lattice, a strong irreducibility property of the lattice. But moreover, we want the H2 action to be strongly ergodic. So there should not even be approximately invariant, H2 invariant subsets. And these properties are enough to establish the essential Cocycle superrigidity property. So a good remark to make here is that when G is in the very specific case where G is compact and totally disconnected, what we recover is exactly a theorem that was proven before by Daniel together with Adrian Ioana and Jesse Peterson. And it's also kind of related to work of Adrian Ioana and work of Caborio, Ioana, and Tucker Drope that I will not discuss here. Let me rather give you the prototype example to illustrate everything, to already show why 2 primes pop up. It will not show you why 1 prime doesn't work, that I will explain later, but why 2 primes pop up? Well, that's exactly the setup that works for this theorem. Because if you add to Z the inverse of P and the inverse of Q, 2 different primes, well, here is the lattice. So it's an arithmetic lattice. If you take the group SL2R and then SL2QP and SL2 of QQ, then the diagonal embedding of this group is, as you know, a lattice. And then we have to look at these conditions here. So you have to take the homogeneous space, the quotient by gamma. This is a probability space. You take its L2 space, and you take the orthogonal complement of constant functions. And in order to get strong ergodicity, what you need, or what you would like to have, it's even stronger, is that this unitary representation of SL2 of QP and SL2 of QQ does not weakly contain the trivial representation. Now, that's something that has been extremely well studied. For this specific case with SL2, it goes all the way back to Gilbert and Jacquet in work on automorphic representations, because this is what they would call automorphic representations, of course, those that are contained in this L2 space. And it follows from that such representations do not weakly contain the trivial, and it does give you the assumptions here. So we have exactly the decomposition in an H1 and an H2, with both acting ergodically and both actually acting strongly ergodically in this case. And therefore, by the theorem, this will be a essentially Cocycle superrigid inclusion. Now, of course, this is more like an example. This fits into a broad class of examples, and let me just quote you a few. Of course, you would then need more than the old work on automorphic representations, and actually you have to go all the way to Clausel's proof of property tau in high generality for such arithmetic lattices, and then you can cover all kinds of inclusions. So as I said, you can take SLN Z to which I add enough primes into SLN R, and this is a bit of a silly statement. It means that if n is 2, you have to add at least 2 primes, and when n is 3, it suffices to add 1 prime, yeah? But you can also do it with SLN over a ring of integers of a real algebraic number field. So if K is such a real algebraic number field, you have the ring of integers, you have this dense subgroup. And again, in a way, there should be sufficiently high rank. So here, the proper assumption is you look at the number of real embeddings of the field and the number of complex embeddings. And then there is a condition to be satisfied that ensures the Cocycle superrigidity property. And then you can push this much further to general as arithmetic groups and in particular this kind, subgroups of this kind of Lie groups. Yeah. Now, what I will explain towards the end is why there are two examples that do not work. As I said, if you only add one prime, there is no Cocycle superrigidity at all. And also in the same vein, I mean, if you look, can very quickly see what are the cases that are not covered here. You see, for instance, if n is 2, and if I would just have the quadratic number field, it doesn't fit here. And indeed, this then subgroup is not Cocycle superrigid at all. And I will show you why. What is the phenomenon behind? Okay, but let me first give you very quickly the main idea to prove the general theorem. So here's the general theorem again. We have a lattice. Here I should add that H is compactly generated. We have the necessary strong ergodicity assumption, and we have to prove that the translation of gamma 0 on G is Cocycle superrigid, and gamma 0 is this projection of gamma on the first variable on G. Yeah? Okay, so here is a basic remark to make. As I already said, when a group is acting on itself, we consider this as like one point. Yeah, and in the same story, it's very easy to see that if you have a locally compact group G and a closed subgroup L, then a one cocycle for the translation action is always trivial. It's cohomologous to just the constant function equal to the neutral element. Yeah, but that's a triviality. Now it does allow for a change of point of view. So to make the notation transparent, we will rather view the discrete groups gamma and gamma 0 as acting by right translation. Of course, that doesn't matter, but it will help for the notation. So now assume that we are given a one cocycle with values in any countable group lambda, and I have to prove you why it is essentially cohomologous to a group homomorphism from gamma 0 to lambda. Well, thanks to this kind of easy remark at the start, such a one cocycle is actually essentially the same as a one cocycle for the action of this group on G times H, where gamma is acting on the right and H is acting on the left in this variable. Because you see, H is acting like by translation on itself, so you can actually mod it out. And if you mod it out, what remains is really gamma 0 acting on G. Yeah? So that's just a dictionary to say that this is essentially the same data. But now gamma is acting, of course, at the right as a closed subgroup. So it's also essentially the same as H acting on the left on this probability space, G times H mod gamma. Now here we have created room for deformation, because now not only H is acting, but also G is acting. And it somehow has this same flavor of Joanna's proof for compact groups, because for every group element G, you get a new one cocycle, omega prime G, because G is commuting with the H action with this kind of straightforward formula. And again, there is enough of rigidity assumption to have that omega prime G will be cohomologous to omega prime if G is close enough to the identity. So here I did create for you an open subgroup because it will be the subgroup generated by this neighborhood. But then you feel, since I know things on a neighborhood, I have to analyze what happens if I return in a cycle. So there will be some covering, you feel it come, and therefore you only get to essential cocycle superrigidity, and you have to work. Yeah. But that's the main idea. So far for the cocycle part of the story. Let me also say a few words about uniqueness of Cartan subalgebras in these cross products. So it's a very general question one may ask. Yeah? If I give you a free and ergodic action, preserving sets of measure 0, is L infinity of X up to unitary conjugacy the only Cartan? This is typically a very hard question, because actually the first theorem proving such a phenomenon is only obtained in 2007 by Takaozawa and Sorin Popa, who proved that the answer is, for instance, yes, if gamma is a free group and if the action is profinite, so an inverse limit of actions on finite sets. Now, several years later, Sorin and I could generalize this and prove that actually when the free group acts in any way, need not be profinite, then such a cross product always has a unique Cartan subalgebra for probability measure preserving actions. And that's, of course, essential. And then since then, I mean, gradually this kind of property that we coined Cartan rigidity has been proven for more and more families of groups. Now we are looking at infinite measure preserving actions, and therefore you have to be a little bit more careful. For instance, it's never true that for an arbitrary infinite measure preserving action, you have uniqueness of Cartan, because you could, for instance, choose an amenable action. And then your cross product will be an injective factor, and there is no uniqueness of Cartan up to unitary conjugacy at all. So you need not only look at the group, but also the way it acts. But here, this action on the hyperbolic plane is of a very specific nature. So I can actually view it in a completely different way, well, completely different, in a different way, and deduce in that way that Cartan must be unique. So what happens? Assume that you add a finite number of primes to Z, so that gamma becomes a lattice in PSL2R times the product of these QPs, PSL2 of QP, as we have seen before. Now the hyperbolic plane is G mod K, where K is PSL2. And then actually it's not very hard to see that we can again play with this left and right modding out with closed subgroups, that this to infinity factor is actually isomorphic in a canonical way to the to infinity factor that arises from this locally compact group acting on this probability space. So you have G times H mod gamma, which is a probability space. K is a compact group acting on G, so you can still mod out by a compact group. That's not a problem. And we do get a cross product of a probability measure preserving action of this locally compact group H. Now, also locally compact groups may satisfy Cartan rigidity for probability measure preserving actions, once more. And this kind of group does fit into the framework. If you take a finite product of such PSL2s, it's very much a bit of this free group flavor, rank 1 phenomenon, if you wish. We do get for these groups, for instance, automatic uniqueness of Cartan. Now here there is a big warning, if you would wonder. Of course, L infinity of X in this picture is not a Cartan subalgebra. So there is a Cartan, it's kind of canonical. It comes from choosing a cross section. I will come to that at the end. But it's not because H is not discrete. I mean, it's not L infinity of X itself that is the Cartan subalgebra, but there is a unique one. Okay. So that deals then with uniqueness of Cartan. So that means that now in the main result, so here is again the theorem that I showed you on the first slide. So if you add finitely many primes to Z and you take PSL2 acting on the hyperbolic plane, if I add no primes, there is a fundamental domain. That's a triviality. If I add at least 2 primes, I have sketched 2 things. I have sketched why the cross product has a unique Cartan, and I have sketched Cocycle superrigidity, and therefore we have this W star superrigidity phenomenon. If the same to infinity factor is a cross product, it must be with the same group and the same action, essentially. But that remains then to discuss the middle case. If I just add 1 prime, we have a non-trivial situation. We have a non-amenable factor, but still it's not rigid at all. So what is happening here? And what is happening here, so this is the specific case. What happens with this group action? Well, actually it's an observation, but you have to take the good point of view that the orbit equivalence relation is so-called treeable. Now I will on the next slide give you the formal definition of a treeable equivalence relation. But it has a consequence, as I will also explain on the next slide, due to Greg Yort. And a consequence is, it's not very explicit, of course, but one can prove that therefore in the hyperbolic plane, I can choose a set of positive and finite measure. And on that set, I can choose a measure-preserving action of the free group, F2, in such a way that the orbit relation restricted to that part, so I look at the orbits under gamma, but only within X, is actually the orbit relation of F2. That's a consequence of treeability. Now, F2 is very much non-rigid, because a consequence of this is that my cross product happens to be the cross product of this F2 action infinitely amplified. And then, of course, cross products with F2, they are highly non-rigid, because you can take any amenable group lambda 1, any amenable group lambda 2, and act with the same orbits, because an amenable group always acts with the same orbits as a Z action by the Kohn-Feldman-Vaes and Ornstein-Vaes theorems. So therefore, there is always, once it's an F2 action, there is a total absence of rigidity. Okay, so what is this notion of treeability? So treeability goes back to Adams, an accountable and non-singular, so measure class preserving equivalence relation is called treeable if you can choose a treeing. Now, before I explain you what is a treeing, you should look at the obvious example. So the obvious example is really the orbit relation for an action of a free group. If you have an action of the free group, its Cayley graph is a tree. And then, of course, the group is acting, and you look at the orbit. So every orbit inherits from the Cayley tree a tree structure on the orbit. Now, that you can express on the level of the equivalence relation. You say that an equivalence relation is treeable if you can choose a Borel subset, T, in the relation, so that T is now also a subset of X times X. So really formally, I can view this as edges of a graph with vertex set X. And what I require is that this just equips me in this Borel way, gives every orbit of the relation, every equivalence class of the relation, the structure of a tree, of a connected tree. Now, this is the obvious example. And actually, these are essentially the only examples, because that's a truly non-trivial theorem, actually, of Greg-Yort, that essentially the only treeable equivalence relations come from free actions of the free group. So if R is, of course, if R would be amenable, it's always treeable, and you get a Z action, that's the kind of silly case. But if you have a non-amenable treeable equivalence relation, and if mu is either a finite or infinite invariant measure, then at least on a Borel subset of positive measure, you may choose a free action of the free group such that the orbits of that free action is precisely the restriction of R to my non-negligible part. So you have to leave a little bit of room. So you restrict your equivalence relation to a non-negligible subset, and on that non-negligible subset, it is the orbit relation of a free action of a free group. And actually, you cannot do really better than this, because there is Gaboriau's notion of cost and of equivalence relations, and such an equivalence relation would have cost n. Now, there are equivalence relations where the cost is not an integer. So you have to first restrict to a subset where the cost would then become an integer, say n, and then Fn can act there. Yeah? So it's really essential that you take the liberty to restrict to a subset. Okay, now what about the connection to my main example? Because I should now go back to my SL2 Z1 over P. And for this, we will need treeability, but now for locally compact groups. And that's a kind of only recently studied notion, although the versions of the paper and certainly results in talks were present since a few years already. So there is work of Conley, Gaboriau, Marx, and Tucker-Drobe, kind of recently. And the notion is the notion of strong treeability for a locally compact group. And the notion is saying that a locally compact group is strongly treeable if for every free and probability measure preserving action of that group, the so-called cross-section equivalence relation is treeable. Now, what is such a cross-section equivalence relation? I would like to look at the orbit equivalence relation, but I want equivalence relations with countable equivalence classes. So I have to do a little bit of measure theoretic magic. So what is a cross-section? A cross-section is a Borel set with the property that there is a neighborhood of the identity in my locally compact group, such that when I restrict the action to that neighborhood and to my Borel set, this map becomes injective. And Y is not too small in the sense that H acting, the orbits of U under H, the saturation in that way, as a complement of measure 0. Now, such a thing always exists. That's not completely trivial. It always exists, and it does induce on Y. I can restrict the orbit relation to Y, and that induces a countable equivalence relation on Y. And that's the way in which actually even actions of locally compact groups give rise to countable equivalence relations and give rise in a canonical way to Cartan subalgebras in the cross product. Now, this exactly applies to PSL2 of QP. It's not very hard to see that PSL2 of QP is strongly treeable. I mean, the Basser tree is almost jumping in the ice. Again, by this dictionary of passing from discrete groups to their locally compact ambient groups, the orbit relation of PSL2 Z1 over P acting on H2 will actually be stably isomorphic to the cross-section equivalence relation of an action of this group, and therefore it's a treeable equivalence relation and has no rigidity. Now, the recent paper of Conley, Gaboriau, Marx, and Tucker-Drope shows that also PSL2R is strongly treeable, which is actually a highly non-trivial theorem. And that then gives you that also this equivalence relation is treeable, can thus locally be implemented by a free group free action. And therefore also that example has no rigidity at all. And that's what I wanted to tell you. Thank you.
Thank you for a very nice lecture. Questions, comments?
Yes, I have one question. I mean, one comment and one question. I presume that your method also covers the case of the Ziegel upper half space.
So for Cocycle superrigidity, this is probably true. Yes. Now, the uniqueness of Cartan is much more delicate to see whether this is still covered. So I should look at the details then.
Okay. And my second question is the following. Somehow, you know, it would be nice to be able to recover directly a lot of additional structure from the equivalence relation and so on, like, for instance, the complex structure in the case of the upper half plane, without resorting to the theorem. You see what I am saying?
Sure.
So, I mean, so in some way, what one would like to do in the rigid case is to climb the stairs of the structure I mean, of course, the best would be to get a spectral triple at the end of the day or something like that, which is coming just from the measure theory. I mean, that would be, you know, really, and in a way, this is pretty much what was done in the Margulis framework, because, okay, I mean, gradually, of course, it was rather different, but so, I mean, that's more general question than a specific one, but
yeah, that, of course, I have no idea how to do something like that, but you're absolutely right. I mean, in principle, it's there, so maybe
in principle is there.
Yeah,
it is there,
exactly.
You know,
yeah.
So yeah. Also, I have just a stupid thing. This cross-section equivalence relation, it would be shorter to call it a transversal, I would say.
That's true. Yes, that's also it. Yeah, I totally agree. I should have said it. I mean, it became common to call it like that, but the transversal is a much better word. And of course, it goes back to what you did for foliations.
Yeah, at least it's shorter. I mean, you know, it's
Yeah,
good to
yeah,
have a
yeah.
short word. Yes.
Any more questions? Actually, just one thing. So, apropos Alan's question. So, for your example with number of primes, so number of primes seem to be some kind of invariant of your Von-Neumann algebra.
That's also true, yes.
Yeah, an idea where it comes from.
Well, that's actually even part of, there are certain much more general phenomena where you have this kind of, first of all, rank one behavior, like in anything that vaguely resembles SL2R. And then if you take a finite product of these, then you recover the number of factors that you have taken. And somehow the number of primes that you add to Z is then in this lattice setting recovered from the number of direct factors that you need. And therefore, yeah, there are much more general frameworks where you can prove that certain von Neumann algebras can only be decomposed using that number of direct product factors or things like that. Yeah.
So something like factorization. Okay.
Yeah. Yeah.
Okay. Thank you. That doesn't seem to be any more questions. Okay, there doesn't seem to be any more questions. So, Stefaan, thank you for the beautiful lecture.
Thank you very much, Richard.
And at least I learned a lot.
Thank you.
So let's thank Stefaan again.
Okay, thank you.
Thank you.
See you soon.
See you soon. See you in 2 weeks' time. Bye.
Okay. Bye.
Bye.
Bye.